In the silent, unending theater of the cosmos, a message is traveling. It has been journeying across the void for 54 million years, a final ghostly whisper from a star that no longer exists. This communiqué is not written in language, nor is it carried on sound waves. It is inscribed in the very fabric of light itself, a secret code hidden within the torrent of photons unleashed by a Titan's death. For millennia, we have looked up at the stars and seen them as perfect, placid points of light. We imagined their deaths when they came would be equally perfect, a symmetric, spherical bloom of celestial fire expanding into the darkness. But this ancient message arriving now at our planetary doorstep tells a different story. It speaks of a violent, chaotic, and breathtakingly misshapen demise. This is the story of Supernova 2024ggi and the revolutionary first glimpse into the true shape of a star's final explosive moment. Our chronicle begins not in the depths of space but here on Earth. On an otherwise unremarkable night, a network of robotic eyes swivels across the heavens. These unsleeping sentinels are programmed for a single profound purpose: to notice change in a universe that appears to our fleeting perception eternal and static. They tirelessly compare fresh images of the sky with archival data, searching for the one new pinprick of luminescence that signals a cosmic event. Deep within the constellation Hydra, nestled in the graceful spiral arm of galaxy NGC 3621, an algorithm flags an anomaly. A new star has appeared where none was before. An automated alert flashes across computer screens in observatories around the globe. The astronomical community galvanizes. The hunt is on. The new celestial object is designated 2024ggi. It is a supernova, the cataclysmic self-immolation of a massive star. For astronomers, the appearance of a new stellar detonation is always a momentous occasion, but this one holds a particular, almost desperate urgency. It is relatively close, cosmically speaking, allowing for unprecedented detail, and it has been caught early, exceptionally early. The light reaching Earth is from the very first day of the explosion, the raw, unfiltered chaos of the initial shockwave tearing through the star's outer layers. A team of scientists who have waited a professional lifetime for such an opportunity know that this is their chance to witness the genesis of a cosmic ghost. They race against time, not because the supernova will fade, but because the most vital clues are the most ephemeral. The initial moments of these titanic blasts hold the key to their fundamental physics, and that primordial information is quickly obscured by expanding clouds of debris. Their goal is to capture something more esoteric than a simple image. They seek to measure a subtle, almost imperceptible property of the incoming radiation. A quality of light that our eyes cannot detect but which carries profound information. They are hunting for polarization. To understand this crucial clue, we must first reconsider the nature of light itself. Imagine light not as a simple ray but as a wave rippling through space-time. Like a wave on the surface of a pond, it oscillates. It moves up and down. But unlike a pond wave, a light wave can also oscillate side to side or at any diagonal angle. The light from an ordinary source like a light bulb or the sun is a chaotic jumble of these waves. Photons are vibrating in every conceivable direction, a disorganized, random mess. This is unpolarized light. Now, picture a vast cosmic picket fence. This fence has slats that are all aligned in one direction, say vertically. If you were to throw 1,000 skipping ropes at this fence, each one wiggling and undulating in a random orientation, only the ropes happening to wiggle vertically would pass cleanly through the slats. The ropes wiggling horizontally would be blocked. Those wiggling diagonally would be partially obstructed. The light that successfully passes through this metaphorical fence is now ordered. All its waves are oscillating in the same plane. It has become polarized. In the universe, there are no literal picket fences. Instead, nature provides a far more elegant filter, tiny particles like electrons. When light from a distant source scatters off a cloud of electrons, it can become polarized, its vibrations aligned in a specific direction. The key insight is this: if the source of light is perfectly spherically symmetrical, and it is surrounded by a perfectly spherical cloud of scattering material, all the individual polarizations will cancel each other out. The net result from our distant vantage point would be zero polarization. We would receive a jumbled random signal telling us nothing about the geometry of the event. But what if the event was not symmetrical? What if the exploding star was shaped not like a perfect marble, but more like a squashed ball, or even a dumbbell? In that case, the light scattering off its lopsided shell of gas would not cancel it out. More light would be scattered in certain directions than in others. The resulting waves traveling across millions of light years would carry a distinct measurable polarization signal. A net alignment of their oscillations would survive the immense journey. This signal would be a ghostly imprint of the explosion's true shape, a direct measurement of its asymmetry, its deviation from perfect uniformity. For decades, this was the holy grail of supernova research. Theorists suspected that these stellar detonations were not the neat spheres of textbooks, but their models lacked the definitive proof that only direct observation could provide. Capturing that faint, polarized signal from the fiery birth of a supernova was the dream. A dream that with 2024ggi was about to become an astonishing reality. This quest to decode the hidden messages in light is a profoundly human endeavor, one that stretches back centuries long before the concept of supernovae was ever imagined. In the early 19th century, the French physicist Étienne-Louis, gazing at the reflection of the setting sun in the windows of a Parisian palace, looked through a crystal of Iceland spar, a naturally polarizing material. He was stunned to find that as he rotated the crystal, the reflected image of the sun dimmed and brightened. He had discovered that reflected light was polarized. The simple act of bouncing off a surface had organized the light waves, forcing them into a preferred orientation just like our cosmic picket fence. This was the dawn of a new science, a new way of interrogating reality. Yet for over a century, this phenomenon remained largely a laboratory curiosity. Simultaneously, on a completely different intellectual path, our perception of the heavens was transforming. For millennia, the celestial sphere was considered a domain of divine perfection and immutability. This ancient conviction was first shattered in 1572. The Danish astronomer Tycho Brahe, a giant of observational science, recorded the appearance of a dazzling new star in the constellation Cassiopeia. It was brighter than Venus, visible even in daylight. By meticulously measuring its position, he proved it was far beyond the moon, located in the realm of the supposedly unchanging fixed stars. The heavens were not static. They were dynamic, violent, and capable of startling novelty. Another such guest star, as Chinese astronomers had called a similar apparition in 1054, was observed by Johannes Kepler in 1604, further cementing this revolutionary idea. These were the first supernovae of the modern scientific era, celestial catastrophes that tore down the walls of ancient cosmology. But what they were remained a profound mystery. It would take another 300 years for the puzzle pieces to begin falling into place. In the 1,930 seconds, the brilliant Indian-American astrophysicist Subramanian Chandrasekhar calculated that a dying star above a certain mass could not support itself against its own gravity. It was doomed to a catastrophic collapse. Around the same time, astronomers Walter Bade and Fritz Zwicky, studying these new stars, coined the term supernova and proposed a breathtakingly audacious theory. They suggested these explosions were the result of a normal star collapsing into a hyperdense neutron star, releasing an unimaginable quantity of energy in the process. An entire star, in its final moments, becoming a single, city-sized atomic nucleus. The concept was so outlandish it was largely ignored for decades, yet their core intuition was correct, and for the rest of the 20th century, our models, both theoretical and computational, treated these colossal events with a simplifying assumption that they were spherical. It was easier to calculate, it was elegant, it just seemed to make sense. But a nagging suspicion remained that the universe was messier and far more interesting. Now, these two great streams of scientific inquiry, the esoteric study of polarized light and the dramatic investigation of stellar death, were about to converge spectacularly. Aboard a state-of-the-art telescope, a specialized instrument called a polarimeter was pointed towards the nascent glow of 2024ggi. Inside this device, a series of advanced filters and detectors, the modern descendants of Malus's simple calcite crystal, began the delicate process of dissecting the incoming photons. The team watched their screens, their collective breath held. The data began to flow, a stream of numbers representing the orientation of light from a cataclysm that occurred when the first primitive primates were just beginning to evolve on Earth. The question was simple, but its implications were monumental. Was there a signal, or was there only the random noise of a perfectly spherical blast? To fully appreciate the drama unfolding in that control room, we must first journey back in time and travel across space to visit the star that was. Before it was a supernova, 2024ggi was a red supergiant. For millions of years, it had lived a relatively stable existence, a colossal nuclear furnace fusing hydrogen into helium in its core. But it was a behemoth born with more than 8 times the mass of our own Sunday. And for such titans, life is fast and death is inevitable. Having exhausted the hydrogen fuel in its core, it began to fuse helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon. With each new stage of fusion, the star's internal clock ticked faster. The hydrogen-burning phase lasted millions of years. The final frantic stage of silicon burning would last only a single day. During this time, the star swelled to monstrous proportions. If placed at the center of our solar system, its outer layers would have engulfed the orbit of Mars, perhaps even Jupiter. It became a vast, diffuse, and intensely luminous object, its surface churning with violent convection cells the size of entire solar systems. It was a star already on life support. Its structure, a delicate, layered onion of progressively heavier elements, all balanced precariously on the brink of collapse. At the very center of this celestial giant was a core of inert iron. Iron is the ultimate nuclear ash. Fusing it into heavier elements does not release energy, it consumes it. The furnace at the heart of the star, which had held gravity at bay for eons, finally went out. In less than a second, the equilibrium was shattered. Gravity, the universe's most relentless force, won its final victory. The iron core, with a mass greater than our sun but compressed into a sphere the size of Earth, began to collapse under its own staggering weight. The implosion was breathtakingly swift. Within a quarter of a second, the core shrank from the size of a planet to the size of a city. Protons and electrons were crushed together to form a sea of pure neutrons. The core became a proto-neutron star, one of the densest forms of matter in the universe. This new, unthinkably rigid object resisted further compression. The infalling outer layers of the star, which had been plummeting inwards at a quarter of the speed of light, slammed into this immovable neutron core. The result was a rebound of unimaginable power. a shockwave of catastrophic proportions was born. This outward propagating front of pure energy and pressure began to tear through the star from the inside out. This is the engine of the supernova. This is the moment of detonation, and it is in the complex, turbulent physics of this moment that the shape of the explosion is forged. Back in the terrestrial observatory, the first plots appeared on the screen. There was no ambiguity, no need for complex statistical analysis. The signal was there. It was strong, clear, and undeniable. The light from Supernova 2024ggi was polarized. A wave of elation and profound discovery washed over the assembled scientists. Decades of theory of speculation of waiting had been validated in an instant. They were the first human beings in history to see with empirical certainty the shape of a supernova during the first 24 hours of its existence, and that shape was not a sphere. The data, when translated into a geometric model, painted a startling picture. The stellar detonation was significantly flattened like a sphere that had been squeezed at its poles. It was an oblate spheroid, an explosion with a distinct preferential axis. It had a defined equator and poles, a cosmic orientation born from the chaos of its formation. This was not the clean, simple death of the textbooks. This was a messy, complex, and directional event. The implications of this single measurement taken on day one are transformative. The discovery of this asymmetry immediately poses a new, deeper question: why? What could cause a star to die in such a lopsided fashion? Several compelling possibilities emerge, each offering a window into the star's secret life. One leading hypothesis involves the star's rotation. Perhaps the progenitor red supergiant was spinning rapidly in its final days. As its core collapsed, the law of conservation of angular momentum would have caused that collapse to happen more readily along the poles of rotation than along the equator. The resulting explosion would then be focused by the star's own spin, blasting outwards with greater force along the path of least resistance, the poles. The result would be a jet-like bipolar explosion which, when viewed from the side, would appear as a flattened asymmetric structure. This single polarization measurement could be a direct echo of the dying star's final spin. Another tantalizing possibility involves the presence of a hidden companion. Many massive stars are not solitary travelers like our Sun. They are born in binary or multiple star systems locked in an intricate gravitational dance. A close companion star could have profoundly influenced the final moments of the progenitor. Its gravitational pull could have stripped away material from the supergiant's outer layers, creating a dense disk of gas, a torus swirling around the star's equator. When the final detonation occurred, the shockwave would have expanded easily into the vacuum above the star's poles, but it would have been constricted and impeded by this dense equatorial ring. The explosion would have been forced into a dumbbell or hourglass shape, its energy funneled outwards in two opposing lobes. The polarized light then becomes a tombstone not just for the one star that died, but for the complex relationship it shared with a neighbor. A third scenario looks not to external forces, but to the internal turmoil of the star itself. In the final centuries before its collapse, a red supergiant does not shed its outer layers uniformly. It can undergo massive eruptive events, casting off huge shells of gas and dust. If this mass loss was not symmetrical, if the star had ejected a dense clump of material in one direction, the subsequent supernova shockwave would ram into this pre-existing structure. The collision would create a brilliant off-center flash, and the entire expanding remnant would be distorted, its shape molded by its environment. The asymmetry of the explosion would not be a feature of the blast itself, but a reflection of the star's own messy, turbulent death throes in the years leading up to the main event. The true cause may be a combination of all these factors, a complex interplay of rotation, companionship, and chaotic mass loss. But the crucial point is that now, for the first time, we have a direct observational tool to probe these phenomena at the very moment they occur. The ability to measure the geometry of a supernova on its first day is like arriving at the scene of a cosmic crime just as it happens, rather than trying to piece together the story from the cold wreckage centuries later. This single observation from 2024ggi has transformed our approach. It proves that the initial conditions, the intimate details of the progenitor system, are not erased by the blast, but are instead imprinted onto the shape of the explosion itself. The light from the fire carries the memory of the spark. This discovery reverberates far beyond the study of a single stellar death. The shape of a supernova has profound consequences for some of the biggest questions in cosmology. We are, as the famous saying goes, made of stardust. Every heavy element in our bodies, the carbon in our cells, the oxygen we breathe, the iron in our blood was forged in the heart of a massive star and then scattered across the galaxy by a supernova explosion. But if these explosions are not spherical, then this enrichment process is not uniform. It means that supernovae distribute their newly synthesized elements directionally. They might inject powerful, concentrated jets of heavy elements into the interstellar medium, seeding some regions of the galaxy with a richer chemical mix than others. The lopsided death of a single star could influence the composition of the next generation of stars and planets that form from its ashes, dictating whether a nascent solar system has the right ingredients for life. Our own chemical inheritance may be the result of a chance encounter with the focused debris from one of these asymmetrical cosmic conflagrations billions of years ago. Furthermore, the outcome of a core collapse supernova is not just a cloud of gas. At the heart of the expanding remnant lies a compact object, either a neutron star or, if the progenitor star was massive enough, a black hole. The asymmetry of the explosion is intimately linked to the birth of these exotic objects. An off-center blast can deliver a powerful kick to the newborn neutron star, sending it hurtling through the galaxy at millions of miles per hour. Astronomers have long observed these high-velocity runaway neutron stars, and the misshapen blast of 2024ggi provides the most direct evidence yet for the mechanism that launches them. The explosion's geometry dictates the destiny of its own remnant. Even the formation of a black hole might be an inherently asymmetrical process, with jets of energy escaping along the poles while the rest of the star succumbs to infinite collapse. By studying the shape of the light, we are studying the mechanics of black hole birth. The early triumph of supernova 2024ggi heralds a new era of transient astronomy. It demonstrates the immense power of rapid response observation. Future observatories both on the ground and in space will be designed with ever more sophisticated polarimeters poised to catch these ephemeral events within hours or even minutes of their first light. We can envision a future where we not only measure the shape of the blast, but map its changing geometry in real time as the shockwave evolves. We could watch the jets form, see the interaction with surrounding material play out, and build a three-dimensional dynamic model of a star's death throes from millions of light-years away. The James Webb Space Telescope, with its incredible sensitivity, could follow up on such events, peering through the dust to see the central engine in unprecedented detail. We stand at the threshold of being able to create complete cradle-to-grave biographies of massive stars from their birth in nebulae through their turbulent lives to a final high-definition film of their explosive departures. Ultimately, the light from 2024ggi does more than just answer scientific questions. It touches upon something far more fundamental, a deep philosophical chord within us. It is a profound reminder of the universe's intricate and often violent beauty. We look out into the cosmos and see a spectacle of creation and destruction on a scale that defies human comprehension. A single star in its final agonizing moment unleashes more energy than our sun will produce in its entire 10 billion year lifetime. And yet, from within that unimaginable chaos, there emerges a hidden order, a distinct structure, a secret geometry written into the very fabric of the blast. It is a universe that is not just powerful, but also subtle and complex. The photons that reached our telescopes from this particular celestial self-immolation began their journey when our world was a vastly different place. They traveled through the silent, expanding darkness as continents drifted, as mountains rose and fell, as entire species evolved and vanished. Their 54 million year voyage ended in the lens of a telescope, in the circuits of a computer, and finally in the mind of a human being. It is an almost impossibly poignant connection across the vast gulf of space-time. We are a species bound to a single fragile planet, our lives measured in fleeting decades. Yet we have built instruments capable of capturing the last whisper of a dying star, and we have developed a language, the language of physics, capable of decoding its final testament. The discovery of 2024ggi's true shape is not just a technical achievement. It is a testament to the power of curiosity, to the relentless human drive to understand. We look to the heavens not just to marvel at its grandeur, but to find the story of our own cosmic origins, a story told in the polarized light of a distant, shattered sun. The message has been received, and we are at last beginning to understand.